Hello, this is the video for problem set 4, task 3, the audio toolkit. And you had a choice in the previous problem set, and you will have choices in upcoming problem sets about whether to work with Turtle or synth.py, our new library for making music using Python. Rather simple music, but music nonetheless. In this task, you'll also be dealing with music, but from a little bit of a different angle. We'll be giving you some .wav files that contain clips from popular songs. And so those clips are just sort of not individual notes with specific pitches, but rather a bunch of sound. And in fact, the way that the computer represents that sound is via a list of numbers. So this task isn't really about music at all. It's really about dealing with lists of numbers. Although, if we can deal with lists of numbers in clever ways, we can do cool things to music by filtering it, by making it sound different. And so what we're going to do is implement some functions that accept lists of numbers as input and generate lists of numbers as output. And these are going to be different audio effects that we're going to implement. So to deal with audio, right, we need to know something about how it's represented. And I just said it's a list of numbers. It's a little bit more complicated than that. Most WAV files have two lists of numbers, one for the left speaker, one for the right. You can have surround sound and other that have more than two channels. These lists are called channels, right? And the numbers in each list are called samples. So one number is a sample. Most of our audio effects are going to work on a single channel, and the starter code is just going to handle processing the channels for us, although some of them are going to work on both channels at once. So we've given you some .wav files in the sounds folder of the starter code that have excerpts from these songs. And those are the files that you'll be processing. They're fairly short so that the processing won't take too long. The typical audio file has 44,100 samples per second of audio. So that's a lot of numbers for Python to store if you have a long audio file. So there's a process file function that we have given you. You don't need to write it yourself. And it takes one of those audio files and processes it using an audio effect. And your job is to write those audio effects. The process file takes three arguments: the path to the file of the audio file to process, the path to the location to write the new audio file, and we've given you some testing code with examples of this, and then the name of the function that will process the audio as a string. And we've defined some variables for those file paths so that you can just use the variables. For each song, we've defined a source path and destination path variable that you can put in as the first and second arguments of process file. And yeah, the process files will come out in the same folder with a _proc suffix in the end of the file name. If you have installed the simple audio library, which you can also install during this problem set, then Python will actually be able to play the sound as well. So here's what you actually have to do. All of these audio effects have to return a new list. They should not modify the list that we are giving you. They should return a new list. So audio effect number 1 is called make softer. It'll make the loudness of your file softer, right? It'll make the file sort of quieter. And so it takes as an argument a channel, which is a list of numbers. It should return a new list where each value has been multiplied by a factor of 0.1. And you might already recognize one of our list processing patterns. It's probably going to be the way to solve this particular function. So the incoming audio should generally be between -1 and 1, right? So it's not just a list of numbers, it's a list of numbers between -1 and 1. as those samples get closer to those extremes, it's louder. By multiplying by 0.1, we're going to shrink it all towards 0, making it softer overall. Now, we don't have to test this function with an entire audio file, right? If I give it these 4 samples, right, which is not enough for me to even hear it, if I try to play an audio file that's only 4 samples, right, that's a tiny fraction of a second. But we can actually, just thinking about how it should work, like this is the output that we should get. So you can test these functions in the console without having to deal with the sounds if you don't want to. All right, that's audio effect number 1, make softer. Audio effect number 2, it also is going to take in a list of numbers, a single channel, and this is called chipmunk because it's going to make everything sound higher. And to do that, what we're actually going to do is take the list of samples and crush it down so it's only half as long. And we're really just going to throw away all the odd numbered samples. So sample 0, we like you, we'll keep you. Sample 1, get out of here. Sample 2, you're great. Sample 3, gone. And by doing this, we'll have an audio clip that's half as long, and that will also sound much higher when you play it. So these are examples of inputs and outputs. Notice that if there's 3 inputs, we'll have 2 outputs. So it's not always strictly half if there's an odd number of inputs. Okay. Audio effect number 3 is called remove vocals. And this is an interesting one. So actually removing the vocals from an audio clip is an incredibly difficult problem. But we can kind of solve the problem by taking advantage of a trick. So if you think about a band on a stage, right? Who's in the center of the stage? It's the singer, usually, right? Not always, but usually. And if the singer is in the center and the other instruments of the band are to the left or to the right or somewhere not in the center, when we record the music using a 2-channel recording, right, a left and a right channel, the singer is going to be the only person that we hear equally in both ears. All the other instruments are going to be more in one ear than another. So to remove the vocals from a track, if it's been recorded in this way where the vocal is centered, what we're going to do is we're going to have 2 channels as arguments, a left channel and a right channel. So 2 arguments, both of them are lists of numbers. And we're going to take the 2 channels and we're going to subtract the right channel from the left channel. So we'll take left and right channels as arguments. We're going to take the second argument and take each of those numbers and subtract it from the corresponding number in the other channel in the first argument. So as an example, 0.1, 0.5, negative 0.2, 0.3, if that's our left channel, and our right channel is negative 0.1, negative 0.6, 0.3, 0.1. By subtraction, so 0.1 minus negative 0.1 is going to be 0.2. 0.5 minus negative 0.6, so plus 0.6 is going to be 1.1. Negative 0.2 minus 0.3 is going to be negative 0.5. And then 0.3 minus 0.1 is going to be 0.2. Notice that it's possible you'll produce a number that is outside of the range negative 1 to 1. And so to account for that, what we're going to do is, in the end, after subtraction, we'll divide all of our results by 2. So each number in the result, we're going to divide it by 2. And that's going to produce a track that's definitely not going outside the boundaries of negative 1 and 1. So here are some examples of how that should work again. And if you call process file on this song The Distance, it actually works reasonably well. It works poorly on some of the other musicians. And even with the cake example, you can hear some of the other instrumentation. So it doesn't do a perfect job, but it's kind of cool that we can use this simple trick to get such a nice effect. All right, audio effect number 4, reverse. So reverse takes a channel and just gives you the same channel backwards, right? All the samples, the first samples at the end, the last samples at the beginning. There's various uses of this audio technique. In some cases, it's even been used to have hidden messages in songs. There's a Wikipedia article that you can check out. Now, there are built-in Python functions. There's a reversed function and a dot reverse method that do this, right? But it would be a little bit boring if you just used one of those. So we require that you do not use those built-in functions and you implement this yourself using a loop. It is not a terribly complicated thing to do, but you'll have to think about what kind of loop you're going to need to do that. So examples, again, this is another function that takes one channel as input, returns one channel as output. Notice that the remove vocals, even though it takes two channels as input, it only returns one channel as output. That's a wrinkle I forgot to mention. All right. Audio effect number 5, two-sample delay. So two-sample delay creates a sort of underwater or muted effect by removing higher pitches in the audio file. And technically it's called a low-pass filter. A filter is so we have a filter term in computer science for a certain accumulation pattern, right? But a filter in audio processing has a different meaning. It's a step that removes parts of the audio signal. So two-sample delay takes a channel and then kind of makes a copy of it and shifts it to the right by 2 samples, so that every sample sort of comes back 2 samples later. And we're going to take that shifted version and add it back to the original channel. Now, when we do this shift, right, if we have a channel 0.1.4, negative 0.1, 0.3, and we shift it by 2 samples, well, the 0.1 goes over here, and the 0.4 goes over here, and these first 2 are sort of question marks. We don't know what those values should be. And the last 2 sort of are gone. They fall off, right? Because we need the shifted version to be the same length. How do we fill these 2 empty spots in the shifted version of the channel? Well, the two-sample delay function has extra arguments to specify what we should fill those spots with. And this gets used by some of the testing code to make sure that when we're doing two-sample delay on little pieces of a longer piece of audio, the samples that fall off of one piece get provided back to the next piece. So there's a parameter called toSampleBack that's used for index 0 of the shifted track, and oneSampleBack used for index 1. Don't get these things confused. Even though they're called toSampleBack and oneSampleBack, toSampleBack actually is the one that is used first. oneSampleBack is used second. So once we have the shifted track, we then add together the original and shifted tracks per sample, right? So 0.1 plus this toSampleBack value of negative 0.9 is negative 0.8. 0.4 plus negative 0.7 is negative 0.3. Negative 0.1 plus, here's the 0.1 that came from 2 samples ago, and it's sort of echoing or coming back here. And the same with the 0.3 and the 0.4. And then, just as we did with the previous filter, because this could produce values up to negative 2 or 2, we're going to divide the results by 2 to make sure that they stay in range of our audio limits of negative 1 and 1. Okay. Notice that two-sample delay should ideally work with lists of size 0 or 2. 0, 1, or 2, right? And that's a tricky thing to get right. Some hints: the algorithm is a little bit complicated. Make sure you understand how the shifted version is generated before you start writing the code. You can indeed use several for loops if you want. As an extra goal, figure out how to do it using exactly one for loop, so that you're not really creating a copy, but you're sort of remembering things cleverly in order to get it to work. And so here are some examples of what the output should be for certain inputs. Notice that there's 3 parameters. There's the channel, and then these 1 sample or 2 sample back and 1 sample back parameters that are needed to compute the correct output. All right. Audio effect 6. Oh yeah. So we had chipmunk that raises the pitch. Now we have an oh yeah effect that drops the pitch down. And in particular, what we're going to do is the opposite of chipmunk. So chipmunk compressed the channel and made it shorter, right? Effectively making everything faster, and faster means higher pitch. But oh yeah is going to slow everything down. And to do that, what we're going to do is we're going to take each of our samples and we're going to add a new sample between them, so that we're going to effectively double the length of the list by doing this. And the new sample that we add is just going to be the average of the 2 samples on either side of it, so that the signal remains a smooth sort of transition in whatever direction it was going. Now, to actually double the length, we need 1 extra value that's going to come in at the beginning. And so that's another argument to the oh yeah function, is the previous sample that comes just before the channel it was given. And we basically use that argument. That argument doesn't really appear in the output, but what it does do is it gets averaged with the first item of the output, and that average appears in the output. So we take the whole channel, we put a sample in between each thing. We've now almost doubled the length, but we need 1 more sample to really double the length. And to do that, we average the first sample with this previous sample that we're given as a separate argument, and that average becomes the last item that we add. Or potentially the first item, depending on which order you do it in. It's first in the list at the end of the day. Okay. So all of the original samples will still be there, but you double the length by adding things in between. This is called interpolation, and it's used in many audio effects. Here are some examples of what output should be like. Notice that there's 2 arguments, right? There's a channel, a list of numbers, and then there's also a previous sample argument. Okay. We're down to our last audio effect that you have to do, which is called crescendo. So crescendo creates a fade in on the audio track for the duration of the song length. And to produce a fade in, what we want to do is have a series of samples that grow from some start point up to but not including an end point, right? You may recognize that language from the range function. And multiply those samples that are growing in value by the samples that we have in the audio, so that towards the beginning things get much smaller, and towards the end they are at a larger value, so that the loudness increases gradually. So if we want to generate 4 samples, right, that grow from point 2 to point 4, so you'll be getting arguments that specify the volume, the start volume and the end volume of the crescendo. We're going to have to generate the right number of samples and put them in even steps. So we go up to but not including the end value, so that would be 0.2, 0.25, 0.3, 0.35, and notice that we would go to 0.4 if we went 1 more time by the same step of 0.05. We take those increasing samples, we multiply them by the original samples at each index, kind of like we did with Make Softer, except it's a varying value that we're multiplying by instead of a constant value. Excuse me. And that's how we get our fade in. The length of the output is always going to match the length of the input, right? So There are 3 arguments now: the channel to modify, the start volume, and the end volume. And the number of samples of the fade in is going to equal the number of samples in the channel. The start volume and end volume are always going to be between 0 and 1, right? That represent a fraction of the original volume. So here, again, are some examples of what the correct result should be for a few different inputs. And that is all the required functions that you have to write. There is a custom function defined in the starter file, and you can create your own audio effect if you wish, but this is not graded. It's entirely optional. Remember when you're doing this that you want to keep your audio numbers between -1 and 1, otherwise potentially you could damage your speakers or your ears. I'm wearing headphones right now, right? That would be potentially bad. Don't add any parameters to custom, otherwise it won't work with the starter code. But the starter code does have an option for using that custom audio effect to process a file, so you can try it out with one of those songs. All right, that's it for the problem set description. Let me go into detail in the rubric briefly, which will go over the same things we just talked about. So, it's back. All functions better be documented. The goal that we keep throwing at you every time. Goal number 2, so results of make softer are correct, right? And then we see a bunch of goals. So make softer, chipmunk, remove vocals, reverse, 2 sample delay. All of these different functions have to have correct results. And in the definitions category, we have make softer has to use a loop. Chipmunk has to use a loop. Remove vocals has to use a loop. Reverse has to use a loop. 2 sample delay has to use a loop. Oh yeah has to use a loop. Crescendo had better use a loop. Reverse, here we say that you shouldn't use the built-in reversed function or the built-in reversed method, right? We said you're not allowed to do those. You do have to use your own loop. It's required to actually correctly return a correct result, although we don't have an explicit one here. For the extra goals, so for each of these functions, it must not modify any of the provided data, and it must return a fresh list. Ooh, it looks like there's an error in the rubric that I need to check out. These F names in brackets are meant to be the name of the function we're talking about. So make softer, etc. Okay. Those goals, you can see, are pretty much there for all of the different processing functions. There's some extra tests of some of the more interesting functions. You can see that the tests for oh yeah are actually all extra tests. And in the definitions, we have some extra goals that you use exactly 1 loop, right? Instead of at least 1 loop, it's exactly 1 loop in all of these different functions, including the complicated ones like 2 sample delay or oh yeah or crescendo. So those are the core and extra goals for this task. Looks like I have a little bit of cleanup to do, but hopefully that's not too hard to understand despite the error. And that is my video for this problem set.